Hey everyone, and welcome back to AI Paper Podcast. Today we're diving into LLM Pretraining with continuous concepts. It's a fascinating new paper from Meta.
Oh yeah, this one really caught my eye.
Yeah, instead of just relying on that next token prediction, these researchers figured out how to inject higher level concepts right into how they're training these models. It's like giving LLMs this boost of abstract thinking. And the results are pretty remarkable.
Yeah, it's a really clever approach. It addresses some of the limitations we've been seeing, with this traditional language modeling.
Right, because predicting the next word in a sequence is powerful, but it doesn't always get that deeper meaning behind the text.
Exactly. This paper goes right into that problem, highlighting how token-level prediction can kind of miss the forest for the trees. You know what I mean?
Yeah.
They even give the example of words like the or a, grammatically important, but not very, semantically rich.
Right.
Just predicting those tokens doesn't really tell you much about the concepts that are actually being discussed.
Okay, so walk me through this. How do they actually manage to inject these continuous concepts?
So the core of their approach, which they call CoCoMix, is this two-step process.
Okay.
First, they use a pre-trained sparse autoencoder to extract meaningful features from the LLM's hidden state. Think of the SAE as like a filter that isolates the core concepts the model is working with.
So it's like the SAE is identifying the thoughts behind the model's processing.
That's a great way to put it. But here's the really cool part. They don't just shove all those concepts into the model. They use an attribution score to figure out which concepts are actually important for predicting the next token. It adds selectivity.
Yeah.
It's like the model is learning to focus its attention.
Hold on, attribution score. Could you break that down a little more? What's being attributed and how?
It's all about understanding the influence of each concept on the model's predictions. The attribution score is basically measuring how much each concept contributes to the final output. Imagine you're trying to bake a cake, and you have a bunch of ingredients. The attribution score tells you which ingredients are essential for the cake's flavor and texture, and which ones you could leave out and it wouldn't make much of a difference.
Got it. So the high attribution concepts, those are the key ingredients, the ones that really shape the flavor of the language that the model generates.
Precisely. And once they have those high attribution concepts, they compress them into a single continuous concept vector.
A concept vector, what is that exactly?
Think of it as like a concentrated representation of the most important ideas that the model is working with at any given moment. This vector gets incorporated into the hidden state, right alongside those traditional word embeddings, like giving the LLM a separate thought bubble, where it can process these abstract ideas before generating the next word.
Oh, I love that analogy. It makes this whole concept vector idea so much easier to grasp. So essentially, they're weaving this additional layer of conceptual understanding directly into the LLM's internal representation of the text.
Exactly. And that two-step process, the concept extraction, and then the integration of that concept vector, that's at the heart of why CoCoMix is getting such remarkable results.
Okay, spill the beans. What kind of results are we talking about? Is this just some theoretical improvement, or are we seeing real-world gains?
This is where it gets really exciting. They found that CoCoMix is not only achieving comparable or better performance than standard next token prediction models, but it's doing it with significantly fewer training tokens.
Fewer tokens in this economy. That's music to my ears. Just how much are we talking about?
So in one of their experiments, they saw a reduction of 21.5% in the number of training tokens needed to achieve the same level of performance.
Wow, that's substantial. And I imagine that has huge implications for training efficiency.
Yeah.
And the overall cost of developing these large language models.
Absolutely. And it gets even more interesting when you look at what they call weak to strong supervision scenarios.
Ooh, that sounds intriguing. Tell me more.
In these scenarios, they use concepts extracted from a smaller, less powerful model to actually train a larger one. It's like taking the distilled wisdom of a smaller model and using it to bootstrap the learning process of a more complex one.
Wait, so you're saying we can take the insights from a smaller, more easily trained model and use them to guide the development of a much larger one?
Yeah.
Wouldn't that lead to limitations from the smaller model, though?
That's a great question. And it's one of the things that they investigated thoroughly. And surprisingly, they found that CoCoMix excels in this area, even outperforming traditional knowledge distillation techniques, which are specifically designed for this type of knowledge transfer.
That's fascinating. It suggests that CoCoMix is able to extract something more fundamental than just the surface level knowledge of the smaller model. It's like tapping into a deeper level of conceptual understanding.
I think you're spot on. And that brings us to another really exciting aspect of this work, the potential for model steerability.
Ooh.
Remember how CoCoMix is working with these explicitly extracted concepts?
The continuous concept vector, right?
Exactly, because they're working with these explicit representations of concepts. It opens up possibilities for influencing the model's output in more predictable ways.
Okay.
They're able to manipulate these concepts to guide the generation process.
So by tweaking those concepts, we can actually nudge the model towards specific outcomes.
You got it. They even ran an experiment where they amplified a specific concept related to website addresses, and both CoCoMix and the original GPT-2 model started generating URLs.
Wow, that's pretty wild. Like they're directly influencing the model's train of thought. By manipulating these concepts, that has huge implications for all sorts of applications.
Yeah.
From content creation to code generation.
Absolutely. It's a step towards making these incredibly powerful models more controllable and interpretable.
Okay, I'm already sold on the potential here, but before we get too carried away, let's take a step back and dive into the nitty-gritty of how they designed and tested CoCoMix.
Sounds good to me. Let's get into the details. One of the things that really impressed me about this paper was how thorough their analysis was. They really went deep into why CoCoMix works so well.
I'm all about those deep dives.
Yeah.
So what was the first thing they wanted to understand?
Well, they started by validating that using the attribution score to select relevant concepts was actually making a difference.
Right, it's like a filter, right? Making sure the model focuses on those most impactful concepts instead of getting overwhelmed by all the noise. So how did they test that?
They compared CoCoMix with a version that used all of the concepts extracted by the SAE without any filtering based on that attribution score.
Okay, that makes sense. A good control experiment, and what did they find?
Well, as you might expect, using that attribution score led to a significant performance boost. It really shows that selectivity in that concept integration process is key.
Okay, so the attribution score is definitely doing its job. What else did they look at?
And the next thing they explored was whether predicting these SAE extracted concepts was actually better than just trying to predict the entire hidden state directly.
Oh, interesting. So instead of breaking down the hidden state into those individual concepts, they tried to predict the whole thing as a single unit. Wouldn't that be simpler?
You would think so, but they actually found that directly predicting the hidden state led to like a noticeable drop in performance. It suggests that decomposing the hidden state into these meaningful concepts is really what unlocks CoCoMix's power.
That's fascinating. So it's not just about adding more information. It's about giving the right kind of information in a way that the model can actually use. It reminds me a little bit of how our brains work. We don't just process raw sensory input. We break it down into meaningful chunks. We break it down into concepts.
That's a great analogy. And it highlights the importance of finding ways to represent knowledge and information in a way that aligns with how intelligent systems, whether they're biological or artificial, actually process and learn.
Right. It's about bridging that gap between the way that we represent information symbolically and the way that these neural networks operate.
Absolutely. And speaking of representations, remember how those predicted concepts get compressed into that single continuous concept vector before being added to the hidden state?
Yeah, it's like distilling the essence of the model's thinking into this single concentrated shot of conceptual information.
Exactly, and the analysis of that compression layer revealed something pretty interesting. They found that the model was selectively compressing the concept information. It's not just blindly squeezing all the concepts together, it's actually learning to prioritize based on relevance.
So the compression process itself is actually another layer of learning and adaptation.
Precisely. And this suggests that the model is developing a more nuanced understanding of the relationship between these abstract concepts and the task of language generation.
Now, this whole idea of transferring knowledge from a smaller model to a larger one, that reminds me a lot of knowledge distillation. Did they compare CoCoMix to that approach?
They did. And they found that CoCoMix consistently outperformed knowledge distillation, particularly in those scenarios where the teacher model was smaller than the student model.
Oh, I'm curious, why do you think that is? Don't both techniques essentially aim to transfer knowledge?
Well, the key difference is in what kind of knowledge is being transferred.
Okay.
Knowledge distillation typically focuses on matching the output probabilities of the teacher and student models. But when that teacher model is weaker, those probabilities might not be the most reliable guide. It's like trying to learn from a teacher who's still figuring things out themselves.
Right, right. So CoCoMix, with its focus on these higher level concepts, might be extracting something more fundamental, something less dependent on the limitations of the teacher model.
That's exactly what the findings suggest. It's like CoCoMix is learning the underlying principles, the core concepts, rather than just mimicking the teacher's behavior.
I remember they also compared CoCoMix to a technique that uses pause tokens. Can you remind us what those are?
Sure. Pause tokens are these special learnable tokens that researchers have been experimenting with. The idea is that they encourage the model to pause and think more before generating that next token.
So it's like creating a more deliberative,
Yeah.
reflective process within the language model.
Yes, exactly. Trying to mimic the way we as humans might pause to gather our thoughts before speaking or writing. So how did CoCoMix stack up against this pause token approach? Well, impressively, CoCoMix came out on top here as well.
Okay, so it's outperforming knowledge distillation,
Yeah.
and even a technique specifically designed to enhance the model's thinking capabilities.
Exactly. Strong evidence that CoCoMix isn't just a clever trick. It's a fundamental advancement in how we think about incorporating concepts into language models.
I'm curious to hear more about the specific architecture and the training details. Did they invent some brand new type of language model, or were they working with something familiar?
They actually opted for a fairly standard GPT-2-based transformer architecture. So this allowed them to directly compare their results with a well-established baseline.
Okay, so no radical architectural innovations. What about the training data? Did they use some massive, never-before-seen data set?
Not at all. They stuck with that classic open web text dataset, the same one used to train the original GPT-2.
Interesting. So same architecture, same data, but with this entirely new concept integration layer. And it's achieving these impressive results.
It is. And to ensure a fair comparison, they carefully match the number of parameters and computational resources across all the models, including the baselines they compared against.
That level of rigor is so important. It gives us confidence that the improvements are truly due to CoCoMix, not some other confounding factor.
Absolutely. And they went even further by providing a ton of additional results and analyses in the appendix, including some really cool examples of how they were able to steer the model's output by manipulating specific concepts.
Okay, I'm definitely going to have to check that out. This paper has given me so much to think about. It feels like we're at a real turning point in AI research, where we're moving beyond just that brute force pattern matching and into a realm where models can actually reason and understand concepts in a more human-like way.
I completely agree. CoCoMix isn't just a clever technical innovation, it's a step towards a more fundamental understanding of how to build truly intelligent systems.
Well said, and that's a perfect note to end on. Thanks for joining me on this deep dive into the world of concept-driven LLMs. Until next time, keep those AI research papers coming.
Okay, my brain is buzzing with all these possibilities, but let's get back to the nuts and bolts of the research for a minute. We talked about these high-level ideas, but I'm curious about the practical details. What were some of the key decisions they made in terms of the model architecture and training process? They actually opted for a pretty standard GPT-2-based transformer architecture. This let them directly compare their results with a well-established baseline.
Right, it makes the findings much more interpretable.
Yeah.
If you're working within a familiar framework, did they stick with the standard GPT-2 setup, or did they tweak things?
They actually experimented with 3 different model sizes, ranging from 69 million to 1.38 billion parameters. This let them see how CoCoMix scaled as the model complexity increased.
Makes sense. Always good to test your ideas across a range of model sizes. What about the training data? Did they use some massive, never-before-seen data set?
Not at all. They stuck with the classic open web text dataset, the same one used to train the original GPT-2.
Interesting. Same architecture, same data, but with this entirely new concept integration layer. And it's getting these impressive results.
It is, and to ensure a fair comparison, they carefully matched the number of parameters and the computational resources across all the models, including the baselines that they compared against.
That level of rigor is really important. It gives us confidence that the improvements they're seeing are truly due to CoCoMix, not some other confounding factor.
Absolutely, and they didn't stop there. For the main results, they trained the models on 200 billion tokens, which took about 382,000 training steps.
Wow, that's a serious commitment to thoroughness. But I remember they also ran some experiments with a smaller training set, right?
You're right. They also ran experiments with the smaller training set of 20 billion tokens, and this was particularly important for those weak to strong supervision scenarios, where they were testing the knowledge transfer capabilities of CoCoMix.
Right, because training a massive model on 200 billion tokens for every experiment just wouldn't be feasible.
Exactly.
Now, there's one more thing I'm curious about. We've been talking about this Sparse Autoencoder, the SAE. as if it's some kind of magical concept extractor. But how was that SAE actually trained?
Excellent question. So they used an open source pre-trained Top-K SAE that was trained on, you guessed it, the same 124 million parameter GPT-2 model.
Makes sense. Everything ties back to that original GPT-2. So they're using the knowledge that's embedded in GPT-2 to extract these concepts and then feeding that knowledge back into the training process.
You got it. It's like this closed loop where the model's essentially learning from itself, but at a higher level of abstraction. And they didn't just train the SAE once and call it a day. They explored different SAE architectures and training procedures to find the most effective approach.
Okay, so it sounds like they really went the extra mile.
Yeah.
To make sure the results were robust and reproducible.
They absolutely did. And to make things even better, they included a ton of additional results and analyses in the appendix, including some really cool examples of how they were able to steer the model's output by manipulating specific concepts.
I'm definitely going to have to dive into that appendix. This paper has given me so much to think about. It feels like we're at a real turning point in AI research. We're starting to move beyond just brute force pattern matching into a realm where models can actually reason and understand concepts in a more human-like way.
I completely agree. CoCoMix isn't just some clever technical innovation. It's a step towards a more fundamental understanding of how to build truly intelligent systems.
Well said. And that's a perfect note to end on. Thanks for joining me on this deep dive into the world of concept-driven LLMs. Until next time, keep those AI research papers coming.